I'm Anil Kumar. With the help of few examples, I'll summarize major characteristics of logarithmic functions in this particular video. It is specially meant for students who are returning back to the university. Let me thank my student Faiza for taking the initiative. We'll talk about relation between exponential and logarithmic functions. Then we'll sketch graphs of different kinds of logarithmic functions and their inverse, which will be like exponential functions. Then we'll take a few transformed logarithmic functions, find their domain and range, and other characteristics as written here. As you know, logarithms are inverse of exponential functions. So it is a good idea to review some basics about exponential functions. Let me begin from there. Let us take a general form. Let's say b to the power of x. Now here b is the base, right? This is the base and x is the exponent. Now for any exponential function, we have few restrictions on base, and the restrictions are that b should be always greater than 0 and b should not be equal to 1. Reason being that if b is 1, then 1 to the power of anything is just 1. It is not exponentially increasing or decreasing. Perfect. And 0 to the power of anything is 0. If I take b as negative, then negative even powers will be positive, odd powers will be negative, so those will be like oscillating, correct? Also, most of these functions will be either always increasing or always decreasing. However, we have no restriction on their domain, right? So as far as domain of this function is concerned, we know that domain, that is the value which x can take, belongs to a real number, and the range of this function is y belongs to real number, and y should always be greater than 0. This is for a basic function represented by b to the power of x. And their graph, if you want to sketch, will look like kind of like this. Let me sketch it here in this fashion, and that is when the power x is greater than 1. If this power is between 0 and 1, that means less than 1 but greater than 0, in that case, you may have a graph which is kind of a decay function, right? So that will happen if x is greater than 0 but is less than 1. So it's kind of a fraction. So this is the kind of graph which you will normally see for an exponential function where x has no restrictions, y, as you can say, range is always greater than 0. So x-axis is basically your asymptote, right? So we have y equals to 0 as asymptote. Perfect. So with this, let us try to now understand logarithmic functions. So I'm taking a few simple examples which will help me to make the connection between logarithmic to exponential and exponential to logarithmic functions, and then we'll evaluate some logarithmic functions, right? So we just saw that if x is written in exponential form, I could write this as b to the power of something, let us say y, and the same thing if I want to write in logarithmic form, I can write this as y equals to log to the base b of x. So these are same statements. They represent exactly the same thing. And to appreciate that, I have taken a few examples. So here we'll write logarithmic form to exponential form, right? So that is, I'm writing in this form. log to the base b of x. That is how you read it, right? So here we have log to the base 2 of 1024 is 10. If I have to write this in exponential form, how do I write? So I retain 10 to the power of 24 here. I can say 10 to the power of 24 is 2 to the power of 10, right? 2 to the power of 10. So the base 2 remains base in exponential form also. Do you see that? So it could be written as 2 to the power of 10 equals to 1024, one and the same thing. The second example is log 100 equals to 2. Whenever we do not mention the base, then by default the base is 10, correct? So now I can write this as 10 to the power of 2 is 100. So let me change the ink. I could write this as 10 to the power of 2 equals to 100. So that becomes the exponential form of this logarithmic form. Do you see the correlation, right? So let me show you once again. So base is 4. In exponential form, base remains same. So I could write this as 4 to the power of minus 3 equals to 1 over 64. Correct? You know exponential functions. This means 1 over 4 cube, which is 1 over 64. Perfect. Now the last one here is for you to do. You can pause the video, answer the question, and then check with my solution. So when I say log to the base 5 of 125 is equals to 3, what I'm trying to say here is that 5 to the power of 3 is 125, correct? That is what it is. So we have got a relation between exponential and logarithmic forms. We maintain the same base. Perfect. Now let's take up the next example in which we will write exponential equation into logarithmic equation, right? So 3 square is 9, you know it. 3 is the base, 2 is the exponent. Now if I have to write this in logarithmic form, I'll maintain the base 3. So I'll say log to the base 3 of 9 is 2. Do you get it? That is how we write it. 2 to the power of minus 3 is 1 over 8. So base is 2, right? So we could write this as log to the base 2 of 1 over 8 is minus 3. That means 2 to the power of minus 3 is 1 over 8. Perfect. Now in this case, the base is 36, right? The base is 36. So we are going to write this as log to the base of 36 of 6 is half. Correct? Last example here is 10 cube equals to 1000. Base is 10. So when the base is 10, we may or may not write 10. So we'll not write 10. It means by default 10. So log to the base 10 of 1000 is equal to 3. So that is how you could actually write down exponential functions as logarithmic functions. Perfect. Now the last example here is to evaluate logarithms, right? So from this knowledge, we will try to evaluate. When we say log to the base 2 of 32 equals to what, we're trying to figure out 2 to the power of what is 32. And we know 2 to the power of 5 is 32. So we get 5 here. 2 to the power of 5 is 32. Correct? Similarly, next one. Log to the base 3 of 81 is what? Now, the other way to look into is that I could write this as log to the base 3 of 81 with base 3, 3 to the power of 4. So 4 becomes my answer. 3 to the power of 4 is 81. Do you see that? This is a very good method of replacing the 81 as a power of 3. Now log to the base 4 of 1 is what? Now as you can see, it has to be 0, since we know anything to the power of 0 is 1. Anything to the power of 0 is 1. 4 to the power of 0 will be 1. So that answer should be 0. Now 5 to the power of what is 1 over 25? It is minus 2. So that is what we get. And that becomes a standard method of evaluating logarithms. Okay, so let's move on further, and now we'll discuss about sketching graph of logarithmic functions and also inverse of those graphs. So we'll take up two examples here. We'll sketch graph of logarithmic functions. We have two examples, log to the base 2 of x and log to the base half of x, correct? So once we sketch logarithmic graph, from there we'll sketch inverse of logarithmic graph. Okay, so log to the base 2 of x, how do we sketch this graph? Well, to sketch logarithmic graphs, what we should do is we have to take some key values into account. For any logarithmic function, whatever the base is, that becomes a very important number to consider. Since we are talking about to the base 2.5, we have a lot of similarities here. So what I will do here is that I'll form a table on the left hand side, and this table may help us for both the examples. Okay, so we'll take up some values of x, and based on those values we'll find what log 2 of x is. We know one thing, that log of 1 is always 0, right? So log of 1 is always 0. Reason is anything to the power of 0 is 1, correct? So you can look the other way, right? So log of 1 is always 0. How about log of 2? If I write the base is 2, so if I take the value 2 here, in that case log 2 of 2 is going to be 1, since 2 to the power of 1 is 2. Do you get it? 2 to the power of 1 is 2. If I take x as, let us say, half, then what happens? So we have to figure out 2 to the power of what is half. We know it is minus 1. 2 to the power of what is half? It is minus 1, right? 2 to the power of minus 1 is half. So that gives you a good view of how the graph may look like. Now if x is very large, that is to say, if x is approaching infinity, then log to the base of anything approaching infinity will also approach infinity. However, we have seen if the value of x is approaching 0, that means 0. Approaching 0 means slightly more than 0. It cannot be 0, right? Since that is not valid, then the graph approaches negative infinity. So these are good values to consider when we sketch logarithmic functions. And it is going to look like kind of like this. Let me sketch this first and then I'll explain. Now in this graph, the point where it crosses the x-axis, where y value is 0, is always 1, correct? Now, when x is equals to 2, when x is the same as the base, which in this case is 2, in that case, log to the base 2 of 2 is 1. So that is very important point to understand. Now the other important point here is half, so which we wrote here. So if it is half the value, in that case, the result is going to be minus 1. Since we know that, let's go the other way, exponential form, to be very clear. If I write 2 to the power of minus 1, we know it is half, correct? 2 to the power of 0 is 1, 2 to the power of 1 is 1. Do you see that? So if you look into the exponential form, things become simpler. So always, whenever you're sketching logarithmic functions, you should take these 3 points, which relate to base, right? In this case, it is 2. Then 1 over base and 1. And the other 2 points are x approaching 0 from the positive side and infinitely large number. That will give you the function itself. Okay. So we've done the first part of sketching the logarithmic function. Now the idea is how to sketch the inverse of this function. Correct? To sketch the inverse of the function, what we can do is that we can sketch a line y equals to x and then reflect it on that line. So I'm now sketching line which is y equals to x. And we are going to reflect this. So once you reflect, this point will coincide with that. Perfect. Now here it will go as far away as it is. So 2, 1 becomes 1, 2. Do you see that? So this point becomes 1, 2. 2, 1 becomes 1, 2. The vertical asymptotes becomes the horizontal asymptote, right? And therefore, what we get is a graph which will look like this. So that becomes the graph of exponential function y equals to 2 to the power of x. So that is how they are related. Now let's do this exercise for the other function also. So here, the important points which we took here, we'll make a table this time horizontally like this. I hope that saves more space and things are clear better here. So we'll take up the values for x. X values, as I was suggesting, approaching 0 from positive side, right? So this side. And then since the base is half for us, we'll take a value of x as half, we'll take as 1, and then reciprocal of half, which is 2. And then infinitely large number. Correct? So these are the values which we are now going to take to sketch the function with the base half, right? With the base half. That is what we are going to do. Now, for log to the base of anything, if I have x as 1, then the value should be 0. Since half to the power of 0 is 1. Do you understand? So related like this. Half to the power of what is 1? So we are saying half to the power of what is 1? Half to the power of 0 is equal to 1. Do you see that? So this 0 is the point. Now here we have to see as half to the power of what is half? That is 1, right? Half to the power of 1 is half. Do you get the point? And what is half to the power of 2? Half to the power of 2 is 1 by 4. But we want 2. So half to the power of what will be 2? That is minus 1 will be 2. Is it okay? So half to the power of minus 1 is going to be 2. So we can now sketch this graph. When x is 1, the value is going to be 0, that is the power. When x is half, the value is going to be 1. And when x is 2, in that case, the value is going to be minus 1, right? So half to the power of minus 1 is 2. So that gives you an idea of the graph. So the base half for the logarithmic function will look like this. Correct? And these points are 1. Here it is minus 1, that is plus 1 when the base is half. Correct? Now, and minus 1 at 2, correct? So this minus 1 is at 2. Now to sketch the inverse of this function, we are going to reflect it on the line y equals to x. Right? So when you reflect it, then the vertical asymptote becomes horizontal asymptote, right? And these 2 points will intersect at y equals to x line, this point, correct? And the graph will be going through 1, right? When x is 0, it is anything to the power of 0 is 1, right? So it is going to be kind of like this. So that becomes the graph for half to the power of x. Let me write down here. Let me write in this. So this is the graph for half to the power of x. The exponential form. Is that okay? So that is how we will see the graph of logarithmic functions with exponential functions, correct? Let me take 2 more examples on sketching the graph. So here we will sketch logarithmic function where log is to the base of 10, right? So let us see how to sketch this. X has to be greater than 0. When x is approaching 0, we are approaching minus infinity, right? And the graph will be kind of like this. We'll fill in the values later. Just to give you an idea, this is not to the scale actually, because since it is 10 to the base, if x is 10, I get 1, right? So further down, if this value is 10, then what I get here will be the y value of 1. And at 1, we'll get the x-intercept. So this is not really to the scale. It should have been very, very close. Anyway, so what is important to understand here is that for a value which is same as the base, in that case, we get the value of 1, right? So log of 10 of 10 is 1. Log 10 of 1 is 0, right? And if I write a value which is 1/10, that is to say log of to the base 10 of 1 by 10, I'm going to get minus 1. So if this is very small here, let's say 1/10, in that case, the value which I get will be minus 1. So these 3 points help us to sketch the graph. The other points which we need to consider is when x approaches infinity, then y also approaches infinity, and when x approaches 0 from the positive side, y approaches negative infinity. Do you get it? So that is how your function can be sketched, correct? Now you can always reflect this on y equals to x to get your graph for the inverse of this function. Is it okay? So that is how we'll actually make the inverse of this function, correct? So kind of like this. So the asymptote now vertical changes to horizontal, and we'll have a graph like this. Now let me take up the next example, which is log of minus x. Now applying the transformation rules, since we have the same base, it will look like the same graph as shown here, except for that this graph will be now reflected on the y-axis, and what you're going to see is kind of like this. Is it okay? So that becomes the graph for log of minus x, where this point will be at minus 1, and a point here where y value, the x value is going to be minus 10. Correct? So from these graphs, you can see that the range is all real numbers, right? Range is y belongs to real numbers. However, the domain is restricted. Now, domain in the first case is x belongs to real numbers, where x is greater than 0. When you are reflecting it on the y-axis, then the domain becomes x belongs to real numbers, where x is less than 0. Correct? And in all these cases, you'll find that the x-intercept is at x equals to 1, or in this case minus 1 when you reflect it. Okay, let's move on and take few other graphs. We'll now consider the graph of transformed logarithmic function log to the base 2 of x plus 2 plus 1. We can obtain this graph by transformation. So let us sketch the base function log to the base 2 first, and then we'll translate 2 units to the left and 1 unit up to get the graph of the transformed function, right? So log to the base 2 of x can be sketched like this, where the critical points are, this being 1, and at log, when x is, we are just sketching graph of log 2, log to the base 2 of x, right? First, let us sketch the base graph, and then we'll translate. So at 2, we'll have a point, let's say this is at 2. The value is going to be 1 here, right? And at half, we'll get minus 1. So these are 3 critical points. Then we have the vertical asymptote, and as x approaches infinity, y approaches infinity, right? So that becomes the graph of log to the base 2. If I have to sketch the graph which is log to the base 2 of x plus 2 plus 1, that really means that the transformation is 2 units to left and 1 up, right? So from here, I could go 2 units left. That means this point will move to 1 and 1 to minus 1. 2 units left and 1 up. That means here. Okay. So this point moves here. The other point is at 1 itself. So it goes 2 units to the left and 1 up. So there it goes. And the third point, which we are considering at half, will now be at 2 units left and 1 up. So it comes here as X-Intercept, right? So these are your points which could be connected together to sketch the graph of transformed function. So it will be kind of parallel. And also let me first sketch the vertical asymptote, which will move from 0 to minus 2, right? So let me go to minus 2 and first draw the vertical asymptote. So that becomes the vertical asymptote, and the graph of the function is going to be kind of like this. Correct? So that becomes the graph for the function log to the base 2 of x plus 2 plus 1, where the vertical asymptote is now at x equals to minus 2. So for the new function, we see that the domain changes to x belongs to real numbers, where x is greater than minus 2. Range remains same. Y is a real number for all these functions, correct? So that is how we could actually sketch the graph of transform function by doing two translations. One is translate 2 units left, and second, translate 1 unit up. Right? So these two translations to the original graph will give us the required graph. Correct? So that is how we could actually sketch any transform function of this form. Now, we are almost at the end of this video. We'll consider domain and range of logarithmic functions. So we have two different functions here, log of 25 minus x squared minus 1 and log of 2x minus 6 to the power of minus 2 plus 1. When we talk about domain of the function, we know that the argument, this is called the argument of log, argument should always be positive, right? So 25 minus x squared should be greater than 0. That is kind of very important. So that really means that 25 is greater than x squared, or when we do square root both sides, then square root of 25 should be greater than absolute value of x, right? That is to say, x is between minus 5 and plus 5. So that becomes the domain of the functions, right? That becomes domain of this function. So we can write down domain is between, in interval form, we can write from minus 5 to plus 5. As far as the range is concerned, the function has no restriction at all. The range is y belongs to real numbers, and that remains same for all logarithmic functions, right, without any other restrictions imposed on them. Now for the next function, which is given to us as log 2x plus 6 to the power of minus 2, I can rearrange and write this as minus 2 log of 2x plus 6, right, plus 1. That minus 2 reflects the graph on the x-axis. However, it will not change the range, right? Range is all real numbers. As far as the domain is concerned, we have to make sure that 2x plus 6 is always positive, right? So 2x plus 6 should be greater than 0. Rearranging gives us 2x greater than minus 6, or x is greater than minus 6 by 2. So we get x greater than minus 3. So in this case, the domain of the function is from minus 3 to infinity, right? So that becomes the domain of our function. So that gives you a technique of finding domain and range of logarithmic functions. So argument has to be greater than 0. Now here is the last part of our video, where we'll try to figure out what are the intercepts and what is the equation of asymptotes. We'll again consider two equations. The first one is 5 log x plus 1 minus 2. So let's work on asymptotes first. Asymptotes you can read from the translation. When I say x plus 1, then the asymptote has moved 1 unit left. So it is at x equals to minus 1. Originally it is at x equals to 0. In this case, asymptote has moved 8 units left, right? So here x equals to minus 8 is vertical asymptote. Perfect. Now let's talk about intercepts. Now since the graph has moved to minus 1, here it has moved to minus 8, we expect both x and y intercepts, correct? So we'll calculate both intercepts. So let us first calculate the y-intercept. To calculate y-intercept, we'll substitute x equals to 0. So if I substitute x equals to 0, what do I get? In the first function, I get 5 log of 0 plus 1 minus 2, which is 5 log of 1 minus 2. Log of 1 is 0. So the first part is 0. So we get minus 2. So y-intercept for us in the first case is at y equals to minus 2. Correct? In the second case, if I substitute x equals to 0, what do I get? Let's calculate. For x equals to 0, what I get here is log to the base 2 of 0 plus 8 plus 1. That means log to the base 2 of 8 plus 1. Now 8 is 2 to the power of 3, right? So we could write this as log to the base 2. 8 is 2 to the power of 3. Is it okay? So that gives us the value as 3. So we get 3 plus 1, which is 4. So in the first case, the y-intercept is at x equals to 0, y is equals to minus 2, and here y is equals to 4. So the intercept here, y-intercept here is 0, 4, and in this case it is 0, minus 2. Correct? Now let us see how to find x-intercept. Now for x-intercept, y has to be equal to 0. So that means we have to equate the function to 0 to get the value of x, right? So let's try to figure this out. Now we have 5 log x plus 1 minus 2 equals to 0. So we have to solve for x, correct? We have to solve for x. So to solve for x, we'll take 2 to the right side first. I may have to push this page a bit, right? So then we will do it. So we'll take 2 to the right side. So we get 5 log of x plus 1 equals to 2. Then we'll divide by 5, right? Get log of x plus 1 equals to 2 divided by 5. This is to the base 10. So we can write this as x plus 1 is equals to 2 to the power of 2 over 5, or x is equals to 10 to the power of 2 over 5 minus 1. Do you get that? So that becomes the x-intercept. So I hope you have understood these steps. We're going to repeat these steps for the second function. That will make it absolutely clear, okay? So let's do it again. So again, what we're kind of doing here is we're trying to find x-intercepts, right? X-intercepts means y is 0. So let me rewrite the equation as log to the base 2 of x plus 8 plus 1 equals to 0. So that gives us log to the base 2 of x plus 8 equals to minus 1, right? So that means x plus 8 should be equals to 2 to the power of minus 1, which is half. And x is equals to half minus 8, so which is 1 minus 16 over 2, or minus 15 over 2. Do you see that? So we get a value of x which is minus 15 over 2, or minus 7.5. So x is equals to minus 7.5. Do you see that? So in this case, the x-intercept is at minus 7.50, and here it is at, you may have to calculate this using a calculator, right? So let's write down this value, what this is. Okay, let's calculate this value. So we have 10 to the power of 2 divided by 5, which is some decimal number, minus 1 equals to 1.51. So we can write this as 1.51, y equals to 0, correct? So that is how you can get or calculate x and y intercepts of logarithmic functions. So I hope that is absolutely clear. So we have considered few basic characteristics and shown some calculations to evaluate logarithmic functions and also how to figure out their asymptotes and intercepts and work with transformed logarithmic functions. I'll provide you with links which will give you more practice on logarithmic functions. Feel free to make suggestions and your views, and if you like and subscribe my videos, that'd be great. Thank you and all the best.